the energy method. So again, we start for the energy method, same thing. We start after disturbance. In other words, we disturb this by what? By X. Then we begin to analyze. In other words, let's neglect the what? The delta, the equilibrium thing. But we are looking at disturbance after equilibrium, because the energies that we will be dealing with, they only start to come in after disturbance. Right. When something is vibrating, it has two particular energies. I didn't introduce talking about that, because as I said, we are trying to just recap. Now, as it vibrates, it has motion. So because of that, there is what? Kinetic energy. At the same time, we are displacing it from the equilibrium position. And when you displace it, what happens? There is restoration to come back there. In other words, we are talking of position speaks of what? Potential. So there's displacement from equilibrium. And because of that, we have what? Potential energy. So we can model our expression like when it's like this, there is no damping, no loss of energy. If there is no loss of energy, that means these two become the only two energies in the system. And we can then say the total energy, Ke plus Pe. That's the total energy. Now the principle is, in the absence of damping, which means no loss of energy, this total energy remains constant. It's a constant. In other words, as this thing is moving, there is the equilibrium position. There is the topmost part, there is the lowest part. Right? When it is at this point, it stops and begins to move in the other direction. So at this point, there is no kinetic energy. All the energy is what? Potential energy. Are we together? Then it changes the direction and begins to move backwards. Now, if you now analyze it somewhere there, it's moving, so it has kinetic energy. It's not at the equilibrium position, so it has potential energy. Okay? Then it continues moving and it gets to the equilibrium position. Now, because it's in equilibrium, no potential energy, which means all the energy is what? Kinetic energy. Are we together? Now, because it is in motion, it overshoots. Again, a mixture of kinetic and potential only, mixture, kinetic only, mixture, potential only, and so forth. So the energy is simply changing from one form to the other. No gain, no loss. Are we together? Right. Because there is no loss, it's a constant. Now, if I have a constant and I find the change, what is the change after some time?
There's no change.
There's no change, right? It's like if I give you this book, okay, someone gave me this CD. I was keeping it up to now. How many CDs do I now have?
One.
Still one. If I keep it for 2 more hours, how many will I now have?
One.
It doesn't change because it's a constant. So when I give it back, it's exactly the same CD. Are we together? So if we have this expression and it's constant and we differentiate it, what is the change?
Zero.
The change is 0, ne? So if we say d et with time, we must get a 0. That's the principle for using the energy equation. Now the next thing that we need to do after knowing this is to find the actual expression for the kinetic energy and the actual expression for the potential energy. And we are going to say this. Ke, we know it very much, isn't it? This is the one which everyone knows all the time without thinking. What is that? half mv squared. But because we are smart and we are modeling in x, we are going to say half m
X dot.
Are we together? In the same way, you look at a spring. I'm not going to go into derivations today, but if the other time we did the derivations, but we are not doing that. In the same way, PE is equal to half kx squared without derivation, just by specifying. If you want the derivation, we can talk about that later. It's very simple. Are we together?
Yes.
Right.